Consider the equation y equals ae to the power of 2x, where a is constant. Let's differentiate this function. Well, we know if we differentiate e to the power of something, we just get it back. But then we must multiply by the derivative of the power. The derivative of 2x with respect to x is 2. Now, a is just a constant in front. We leave that in front. So now we see that dy dx is actually 2 times y. ae to the 2x is just y. So we can just write dy dx equals 2y for this here. So we've formed a differential equation whose solution is y equals ae to the 2x. Next, consider the equation y equals a cos 3x plus b sin 3x. Let's get dy dx. Well, if we differentiate the cos function, we get minus sine. By the chain rule, we must then differentiate the angle with respect to x. The derivative of 3x is 3. So we get 3 multiplied by minus a sine 3x. We multiply those two derivatives together by the chain rule. Over here, we see we have a sine function. The derivative of the sine function is cos function. But then we must multiply by the derivative of 3x, which is 3. The constant b is just sits in front. That's just multiplied in front. Let's differentiate this a second time. The derivative of sine is cos, and by the chain rule we differentiate the angle to get 3, so we've 3 times the constant in front. That gives us minus 9a. Over here the derivative of cos is actually minus sine, and differentiating the angle we get 3, so we have 3 times minus 3b, which is minus 9b. But notice now that we can actually factorize minus 9 out of this expression here, and we're left with minus 9 times this expression up here, a cos 3x plus b sin 3x. So we can write this differential equation here as d2y dx2 equals minus 9 times y, minus 9 times this thing. So we have a solution to this differential equation. It's y equals a cos 3x plus b sin 3x, where a and b are any numbers. Next, we're going to get a differential equation satisfied by y equals a hyperbolic cos of 2x plus b times hyperbolic sine of 2x. I'll just say hype cos and hype sine. Well, if we differentiate hype cos, we get hype sine. If we differentiate hype sine, we get hype cos. And we have to apply the chain rule here as well. We differentiate the argument to get 2 here, so we'll have a 2a here. Differentiating this argument here, we get a 2, so that comes to the front, so we have a 2b here. Let's take the second derivative. The derivative of hype sine is hype cos times 2, so 2 times 2a gives us the 4a. Derivative of hype cos is hype sine, so, and we have 2 times 2b is 4b. You see now that we can factorize 4 out of this expression here, and you'll see that it's just 4 times this expression up here. So we can write our differential equation as d2y dx2 equals 4y, and the solution is given by this expression up here. So notice back here that we have a differential equation with just a first derivative, and the solution has just one arbitrary constant a. But this equation here has a second order derivative, so its solution has 2 arbitrary constants a and b, and the same is true for this example that we just did down here. Now in this example we have the second derivative of y with respect to x equals w over 2, which is a constant, times lx minus x squared. W and l are constants. So we want a function y, function of x, such that the second derivative is this thing. So we need to integrate this thing twice. So when we're integrating a constant times something, we just leave the constant to one side. So we w over 2 times the integral of L times x. Well, L is just a constant, so we leave it to one side. We have x to the power of 1, we add 1 to the power to get x to the power of 2, and divide by that new power, which is 2. When we integrate x squared, we get x cubed over 3. And we have our constant of integration. So when we integrate this once, we get the first derivative, dy dx. We need to integrate this a second time. Well, integrate this a second time to get y as a function of x. So we leave the w over 2 to one side, add 1 to the power here to get 3, divide by the new power, so we have 3 times 2 in here, add 1 here, we get 4, and we have 4 times 3 is 12 in the denominator. And if we integrate a constant with respect to x, we get the constant times x, so we get ax, and we get a new constant which we will call b. Now b, of course, can be different from a. B can be any number, just like a can be any number, so we use a different letter for that number. Let's take this example here, dy dx equals 2 times x. Well, we could multiply both sides by dx and then stick an integral sign in front of both sides. The integral of dy is y, the integral of 2x dx is x squared. We add 1 to the power to get 2 and divide by that power. So we 2 over 2x squared. And we have an arbitrary constant which we will call c. Now a function of the form x squared plus c has the shape of a parabola that's symmetrical about the y-axis. The simplest one, I suppose, is when c is naught. We just have the familiar graph of y equals x squared. The parabola symmetric about the y-axis whose vertex is at 0, 0. C can be any arbitrary number, so here we have a family of parabolas for different values of c. Actually, for this situation, c is the y-intercept of the parabola. So when c is minus 3, we have a parabola passing through the point minus 3 on the y-axis. And similarly, situation for all these other parabolas. They have no points in common actually. It might look like the graphs are going to cross at some point, but it turns out that they don't. So no matter what value c is, we get a unique parabola. And for a different value of c, we have a parabola that has no points in common. So if we could consider all values of c, not just these particular ones, we would have a set of parabolas that do not intersect. Now one way to see that two functions of this form for different values of c cannot intersect is to just imagine what would happen if they did intersect. So c1 and c2 are two different values. To find the point of intersection, of course, we can put them equal to each other because the y values are the same. So for this point, the y values has to be the same for both curves. So we can put x squared minus c1 equal to x squared minus c2. But that leads us to the conclusion that c1 equals c2, which is a contradiction, because we started out by assuming that c1 is not equal to c2. As you can see, we have two different graphs here. So when we go to find the point of intersection of these two graphs, we end up showing that the constants must be the same. Suppose we know that y equals 2 when x equals 0. That means our solution passes through the point with coordinates 0, 2. Then we can work out what c must be. So it's on a graph of this form here. So we plug 0 in for x and we get 2 for y. So that tells us that c must equal 2. So we get the unique solution y equals x squared plus 2. Here's another example. We're going to solve the differential equation dy dx equals 3x squared. And the solution satisfies the condition y at x equals 1 equals 4. So we want to solve this to get y as a function of x. So this is straightforward. We just integrate 3x squared with respect to x. And if we integrate 3x squared, we add 1 to the power, we get 3/3 x cubed, or 1x cubed, plus the constant c. So we know that when x is 1, so x is what's inside the brackets here, so y is a function of x, then y is equal to 4. So we plug 1 in for x and 4 in for y. So we get 4 equals 1 plus c. So c must equal 4 minus 1, which is 3. So we get the unique solution y equals x cubed plus 3. So this satisfies the differential equation, because if you differentiate it, you get dy dx equals 3x squared, and that's what we want for our differential equation. Dy dx equals 3x squared. And if you work out y at x equals 1, you will get 4. So if you plug 1 in for x, you get 1 cubed plus 3, which is 4. In this example, we have the differential equation d2y dx2 equals 6x, and we're going to solve it subject to condition A here. Y at x equals 0 is 2, and y at x equals 1 is 3. So let's look at this first condition. So anyway, let's get the general solution to this differential equation. The general solution will involve general numbers a and actually b as well, because this is a second order differential equation. It's got a second derivative in it. So we integrate 6x once to get 3x squared plus an arbitrary constant a. That gives us dy dx. That's the first integral. Integrate again to go from dy dx to y. So we add 1 to the power, so we get 3/3 x cubed, which is 1x cubed. We have a times x, and we have a new constant b. So this is what's called our general solution. But we know that y at x equals 0 is 2. So if we plug in 0 for x, what do we get? Well, we get 0 plus 0 plus b, which is b. And y must equal 2. So 2 equals b. So we found what b is. But we need to find a. So let's look at the second condition here. Y at 1 equals 3. So we plug 1 in for x in the general solution. So we get 1 cubed plus a times 1. And we have plus b, but we found b. We found that b is 2, so we can plug 2 in for b. And y at x equals 1 is 3. So all of this must equal 3. So from this you can see that 3 equals 3 plus a, or a equals 0. So a is 0, b is 2, so we end up with y equals x cubed plus 2. I will skip example B and go to example C. So we have the general solution of the differential equation. It's y equals x cubed plus ax plus b. Now we have different boundary conditions here for part C. We want y at x equals 0 to be 2, so we want to plug 0 in for x and set the result equal to 2. So what do we get here for y at 0? Well, we just get b, and we're given that y at 0 is equal to 2. So now we know that b must equal 2 for these boundary conditions. Now we still need to find a. So far we've found that y equals x squared plus ax plus b, where b is 2. To find a, we use this second boundary condition. Dy dx is 1 when x is 0. So first we get dy dx. So that's going to be 2x plus the derivative of a times x with respect to x is a, which is the coefficient of x is the constant a. The derivative of 2 is 0. Now we're told that dy dx is equal to 1 when x is 0. Now dy dx is a function of x. We could write it like this. We could write dy dx at x equals 0. That's one way. Another way to write it is like this. Dy dx at x equals 0. So we just plug 0 in for x. We get 2 times 0 plus a. That's equal to a. And we're told that dy dx at x equals 0 is 1. Dy dx is equal to 1, so this must equal 1. So we see that a must equal 1. So now we can write down the solution that satisfies the boundary conditions of C. Y equals x squared plus 1x, a is 1, plus b is 2. Finally, let's look at the classification of differential equations. An ordinary differential equation, abbreviated ODE, is any relation between a function of a single variable and its derivatives. So in the examples that we just did, we saw that y is a function of the single variable x. So in all these examples, y is just a function of one variable, x. The order of a differential equation is the order of the highest derivative in the equation. So for example, the order of the highest derivative in this differential equation is 2. So this is called a second order differential equation. The order of the highest derivative in this differential equation here is 1. So this is called a first order differential equation. You don't see the 1 appearing here. We're just taking the first derivative of y with respect to x. So it's a first order differential equation. A differential equation is linear if the dependent variable, which was y in the examples we looked at, and its derivatives, that would be dy dx and d2y dx2, occur to the first power only, and if there are no products involving the dependent variable or its derivatives. So for example, in this differential equation, the dependent variable is y, and it's a second order differential equation, but this derivative is not raised to any power. We don't see d2y dx2 in brackets raised to some power, for example. Another thing we don't see is products involving the dependent variable y with another derivative. We don't see things like y times dy dx, or y squared times d2y dx2. Anyway, we look at some examples. Now, in this first example of a differential equation, we see that the order of the highest derivative is 2. We have the second derivative of y with respect to x. So this is a second order differential equation. Now, we don't see products involving y times dy dx or dy dx times squared, for example. We don't see any of these derivatives in brackets raised to a power, or we don't see the dependent variable y multiplied by any of these derivatives. The dependent variable doesn't actually appear here by itself. So this is an example of a linear second order ordinary differential equation. Now in part B we have a second order differential equation because the order of the highest derivative is 2. We don't have a third order. The order of this derivative in here is 1. However, this differential equation is non-linear because we have a derivative raised to a power, and we don't want that if the equation is to be linear. Now here the highest order derivative is 1, so it's a first order differential equation, and it's linear because we don't see the dependent variable, which is actually x in this case, multiplied by a derivative, or we don't see neither do we see the dependent variable x raised to any power. We just have x to the power of 1 here. That's something I should have mentioned for this first differential equation. We don't see anything like y squared appearing here. We're allowed to have y appearing, but not y to a power or y times a derivative. Similarly here, x can appear, but not x raised to a power or x multiplied by a derivative. So this equation is linear. Now in this equation here, the order of the highest derivative is 1, so it's a first order differential equation. However, the dependent variable y is the argument of the cos function, and actually that makes this equation non-linear, because something that wasn't mentioned earlier is that we can't have y as the argument of some trigonometric function. Finally, we have a first order differential equation, but it's non-linear because the dependent variable is raised to a power.